slides.
It's great. Thanks for having me. I also appreciate Swinya for organization. It was a great pleasure to present my work. My name is Huang. I am a postdoc from NOAA Pacific Marine Environmental Laboratory studying the marine biochemistry. The title of my today's talk is Remote Assessment of Export of Distinct Biogenic Carbon Pools in the Ocean using the biochemical profiling float. This talk will show part of the result in my recent publication in the Global Biochemical Cycles and some preliminary result of my ongoing project. The biologically mediate the transfer of the organic carbon from the surface to depths, commonly referring as to biological carbon pump, play a critical role in regulating the global carbon cycling and Earth's climate. According to the model projection, once the biological carbon pump shut down, the CO2 in the atmosphere will increase by 40%. One of an excellent metric to constrain the strength of biological carbon pump is net community production (NCP), defined as the gross primary production minus community respiration. It represents the amount of the organic carbon available after the food web cycling. Under assumption of the steady state and we integrate over sufficiently long time scale, the NCP can be equal to carbon export. From the elementary perspective, we can either check the drawdown of carbon dioxide, micronutrient, or generation of the oxygen alongside photosynthesis to quantify the NCP. Operationally, the bulk carbon export can be categorized into particulate organic carbon (POC), particulate inorganic carbon (PIC), that is calcium carbonate production, and dissolved organic carbon (DOC). The relative contribution of each pathway to the total carbon export reflect the ecosystem functioning and in turn determine the magnitude and export efficiency of biological carbon pump. The traditional approach to measure the POC is using the sediment trap or Solene-234. The quantification of the DOC export is closely relied on the seasonal change in DOC inventory from the hydrographic cruise. The primary goal of my study is try to push this limit to use the BGC float to partition the export into the distinct biogenic carbon pools. The secondary goal is to see whether we can get some new insight based on this novel approach. A little bit context about the BGC float. The BGC float is a robotic platform carrying a bunch of the biological and chemical sensors. It usually made a profile from surface to 200 meters every 10 days, giving a lifetime about 4 to 6 years. The global distribution of BGC flow has transformed our way to look at the ocean. In my first part of the study, the location is in the Subarctic East Pacific, one of well-characterized transience location in the world ocean. The reason why I choose this region is because there is the seasonal cruise extending from the west coast of Canada to Ocean Station P, which provide the shipboard measurement to validate our float estimate. In this study, I used the BGC flow deployed in August 2018 during the NASA export campaign. This is the fully loaded BGC float, carry a bunch of the sensors, making it possible to concurrent measurement of pH, nitrate, oxygen, backscatter. The POC concentration was estimated from the backscatter signal. We can compute the DIC from the flow measured pH paired with the total alkalinity from the neural algorithm. This panel illustrates the time series of the multiple parameters from the BG3 from observation. The colorful dot represents the discrete sample collected from the 3-board measurement. The good match up in between gives support to the quality control of the flow data. The black line is the mislayer depth. The white line is the euphotic zone, which is relative constancy over the course of year. In the following study, I will integrate the carbon export over the euphotic zone. The time rate of change of the tracer from the flow observation are affected by the multiple processes, including the gas exchange, evaporation, and precipitation at SC interface, the horizontal and vertical mixing, and the biological activity. We can write down the mass balance function like below. We calculate the biological term as a residual from the flow observation, subtracted by the other abiotic processes. As I mentioned earlier, under the right condition, the carbon export, the biological term can be equal to the carbon export. By leveraging the multiple sensor carry on the BGC flow, we can constrain the biological term from the 4 chemical traces: TA, DIC, nitrate, oxygen, and 1 biotical tracer. In general, the biological terms solved from the 4 chemical tracers show a relatively high value in the summer season and low in the winter season, sometimes negative, which suggests that the ecosystem shift from the autotrophy to the heterotrophy state. In principle, the oxygen and the nitrate-based result both include the POM and the DOM production, whereas the DIC and the TA-based result encompass the additional term that is the calcium carbonate production PIC. But one thing was mentioning that the POM term solved from the chemical tracer boundary give us the idea about the total POM production, which can be accumulated in the upper layer or be exported out of euphotic zone. It can be only interpreted as a particle sinking rate when we integrate over a long time scale. However, the POC term solved from the biotical sensor, it tells us the in situ change of the POC inventory in the water as a result of the POC production subtracted by the sinking particle. Therefore, we can compare about the POC term solved between the chemical tracer and the biotical tracer to solve the missing term, that is the real-time POC sinking flux. This slide showing the theoretical formulation to partition the export into the distinct biogenic carbon pools. It includes a lot of equations. I'm not going into the detail. But the main takeaway idea is we can relate the different tracer boundary using the end member ratio of different carbon pool produced to solve many unknown terms. For example, the DIC and the nitrate-based result both include the POM and the DOM production. We can use the end member ratio of POM and the DOM produced to solve the DOC and the POC production. After we solve the POC term from the chemical tracer boundary, we can further link it to the term solved from the biotical tracer to estimate the real POC sinking flux. This panel illustrates the time series of the POM, DOM, and PIC export using this novel approach, which shows strong dynamics. To verify the flow estimate, DOC production shown in blue we compile the POC sample over the same period from the cruise measurement. If we first order attribute the seasonal change of the DOC in the seawater to the biological production, we can get an encouragement agreement of the DOC export between the cruise measurement in red and the float measurement in blue, which support the rationale of our novel approach. Then we can further link the POC term solved from the chemical tracer boundary with the POC term solved from the biooptical sensor to estimate the real-time POC sinking shown in yellow. The balloon initiated in spring. We can observe there is a high DOC production in blue, but a mild POC production in black, and the accumulation of the POC in the upper layer. During these periods, the historical study record the peak abundance of the zooplankton. So I hypothesize that the peak DOC production is probably attributed by the incursion of zooplankton during the breeding. Meanwhile, the strong top-down control will bring down many newly produced POC to the small and suspended POC, reducing the sinking rate, leading to the enrichment of the POC pool in the upper layers. As the bloom progressed, the summer is the most productive season, characterized with a high POC production, strong POC sinking flood. But it's a little bit surprising to me that in such a productive season, there is a decline in DOC production, which probably due to the simultaneous increase in the microbial consumption. The most exciting result is during the fall and winter season. In this region, there is a long-standing mystery, while there is a persistent sinking flux from the sediment trap in the heterotrophy season. By this novel approach, we observe in the harsh winter, there is future with a mild POC production, mild POC sinking rate, but accompanied by an enhancement of DOC consumption, which implied that the heterotrophy state was sustained by the DOC consumption, but it didn't preclude the carbon export. This helped solve the regional conundrum. I further link the real-time POC sinking rate shown in blue was the flow estimate net primary production shown in red to calculate the real-time carbon export shown in the middle panel. We can observe there is a somewhat elevated carbon export efficiency, which is coincident with the increasing fraction of large particle in the seawater observed from the backscatter signal. As you know, the large particle has fast sinking rate, driving the higher carbon efficiency. Another very interesting finding is in the unproductive winter, we still observe a very high carbon export efficiency. This period is coincident with the rapidly deepening of mid-layer depth shown in black line. The implication being that the physical distribution of the particle may underline the mechanism responsible for this high export relation. Let's do a summary for my first part. In this part, we push the limit by leveraging the multiple sensor carry on a BGC flow to partition the export into the distinct carbon pools. The flow estimate result match up well with the three-border measurement, which gives support to the rationale of this novel approach. By using this approach, we reveal the high dynamics of the distinct carbon pool export, which is likely associated with the complex food web dynamics. In the second part, I will introduce a little bit about some preliminary result of my ongoing project. This is the global distribution of the BGC flow with the different color represent the different sensors. As you can see, the Southern Ocean is a region with high density of the outfit BGC flow, making it an ideal place to apply the method I proposed in the first part. As I mentioned earlier, the end-member ratio is a key metric to accurately solve the distinct carbon export ratio. I use the previously compiled POM and DOM data set to solve the meridional variability of the end-member ratio. The red line is the end-member ratio of POM produced, which is derived from the suspended POC to PO end particle. The blue line is end-member ratio of DOM, which is calculated from the seasonal change of the DOC to DON inventory in the upper layer. Then I take advantage of a large number of the BGC flow operating in the Southern Oceans to constrain the biological carbon flux, and then bring the data into every 5 degrees to reproduce the latitude tendency. The blue line represents the biological terms of the backscatter signal, which show a much lower value than the results from the chemical tracer boundary, which indicate that the majority of the newly produced carbon will be exported out of the euphotic zone rather than integrated in the upper layer. I further calculate the CN ratio of the total carbon export from the DIC and the nitrate-based result shown in this slide. I calculate the influence from the calcium carbonate and nitrification, and to get the real CN ratio of the organic carbon production shown in pink light. The CN ratio of the organic carbon nicely fall within the range of end member of the POM and DOM produced, which enable us to further do the partitioning of carbon export. This is a super preliminary result about the meridional pattern of the export in terms of the distinct biogenic carbon pools in the Southern Ocean alongside the latitude. The blue and the gray color represent the carbon export attributed by the POC and the DOC respectively. The red line is the calcium carbonate production, which shows a slightly higher value around 60 degrees Celsius. This region is located near the node Great Calcium Carbonate Belt in the Southern Ocean. The integrated carbon export ratio in the Southern Ocean is about 3.3 petagram carbon per year, with about 60% contributed by POC, 25% attributed by DOC, and the remaining 6% by PIC. But the contribution of the DOC to the total organic carbon varies spatially, with a higher value in the subtropical ocean and the polar regions. Finally, I link the real-time POC sinking flood solved from the combination of chemical and biological tracer boundary, together with the flow estimate net primary production shown in green to estimate the real-time carbon export efficiency shown in the dashed black line. The carbon export ratio range from 5% to 30% with a higher value in the middle regions. Let's do a summary. Because this is still a preliminary result, I don't want to do a strong conclusion. I just end with my talk with some future perspective. Overall, my current study try to develop a novel approach by using the BGC flow to partition the export into the distinct carbon pool. In addition, to put more insight about the ecosystem dynamic, the data can be also used to persistently train and validation of the satellite carbon export algorithm, because the main challenge in the satellite carbon export algorithm is lack of the field data set, event data distribution, and also admission of the key DOC and POC component. So I anticipate this approach can provide a better data set to generate a new satellite algorithm. That's it. I will stop here. I'm happy to take any question.
Thank you. That was awesome. Yeah, it was amazing. Thanks for also explaining what the carbon flux and pools are doing kind of per season. It was really interesting. Does anybody have any questions? Also, I mean, they can put them in the chat too if they wanted to. Yeah, I just realized that, yeah, I still have lots to learn about carbon export and how to use Argo floats. Oh, Pete, sorry. Yeah.
No, that's fine. Thank you very much for the presentation. So could you just recap what you said at the beginning about how you, I think I'm familiar with the methods for calculating, for instance, the change in alkalinity and also the changes in DIC. So is it based, does it use the pH measurements from the float, or is it using some of the like the reanalysis type products? I think it's called canyons, or is it a bit of both?
Yes, the TA estimate is using the Canyon B algorithm by inputting the flow to measure temperature, salinity, and oxygen.
Okay, so it's the oxygen measurements from the float also come into that, but also using the pH measurements.
Right.
Oh, so using estimated alkalinity, measured pH to get the DIC changes.
Exactly.
Yes. Okay. Thank you. And then when you were calculating the carbon to nitrogen ratio in the exported material, you get the carbon content from the POC production or the DIC consumption corrected for calcium carbonate, and then you get the nitrogen content from the consumption of nitrate in the surface waters?
I'm not sure I totally follow your question. Can you repeat?
So there was a slide a bit further down where you had a calculation of the carbon to nitrogen ratio in the, maybe it was a couple back.
Is this slide you are talking about?
Yes, I think so. Yes, yes. So you had, can you say how you get carbon and nitrogen to be able to calculate the ratio?
Regarding the C/N ratio for the bulk carbon export, we calculate from the DIC-based biological term divided by the nitrate-based biological term, and then to account for the influence of the calcium carbonate production, we link the DIC and the TA boundary to solve the amount of the calcium carbonate production, and then remove it. For the nitrogen, I use some data-driven model result to remove the nitrification effect.
Which is probably small in this area, right?
Yeah. In the majority of the region, the nitrification would be small, but I should be mentioned that in the subtropical ocean, as you probably know, nitrification play a critical role in the C/N ratio. If we didn't account that, we probably will miss many nitrate-based biological term production.
Yes. Okay. Great. Thank you.
I think there was a question in the chat. I will ask, what could be the solution to have more accurate carbon export to deep with the Argo floats? Too deep with the Argo floats? I will maybe ask that.
What would be the best solution to
have more accurate carbon
I can explain my question.
Sorry,
sure.
I'm a bit slow.
Maybe easier. What I meant is, you found those challenges that you have, and among them is that there are no measurements for particulate inorganic carbon or the dissolved organic carbon. Actually, dissolved organic carbon, we would think it would not be exported. and it was actually too deep. It's to the depth. I mean, beyond the thermocline. That's what I meant. So
yeah.
Actually, in your point of view, what modifications do we need to do for the Argo floats, or what should be done to have more accurate measurements?
Yeah, this is a very good problem. As you mentioned, the DOC export is not very effective way for export. So if we're looking at the deep ocean, probably the carbon export is dominated by the sinking particle. So if we want to capture the more accurate carbon sinking particle at the depths, the backscatter sensor will be a very robust sensor to do that. But to achieve this goal, we require very high frequent measurement of the backscatter because, you know, the sinking particle will move very fast. But the current typical sampling frequency for the BGC Argo is about 10 days. It's hard to capture the fast sinking rate. So one of the way we can try is to increase the sampling frequency and using the backscatter signal at the depth to calculate the POC sinking flux.
Okay. Thank you so much. And you should probably then test it in tropical environments as well, because there, because of the permanent thermocline and the smaller particles, you may encounter even another challenge.
Yeah, I agree.
Yeah.
Thanks for the suggestion.
Thank you.
All right. I think one last question if there's one, otherwise we wrap up. Right. Well, looking good then. Yeah, thanks to both of the speakers giving some amazing talks. Yeah, I'm really looking forward to see you next week, I guess, for OSM. And yeah, thanks everybody for joining us and asking so many questions. That's really good and it's really encouraging.
Yeah,
all right,
thank you so much for
see you
inviting
for the
us.
next call then. Bye, people.
Yeah, nice meeting everybody. Bye.